Finally, we have operations for program flow. These instructions don't actually do any calculations, but they decide what to do next. So we have two basic kinds, and they are branching and jumping. A branch instruction says the next instruction should be some small offset from the current program counter. And the jump instruction says the next instruction should be some new, fresh program counter unrelated to the current program counter. So these are used in two different contexts. Branching is used for anytime you're making a local decision, right? If you're making a decision like an if-then or a loop, and we're going to go through lots of examples of how these things work and what the branches look like. You make some sort of a comparison, and then based on the result of that comparison, you decide to either do the next instruction or to skip a few instructions or to go back a few instructions, right? You can have the program counter plus some number or the program counter minus some number. Where does that number come from? It's in the immediate field. And then for jump, you're just going to replace the program counter, pardon me, with an entirely new value. And that is going to require us one new format for MIPS instructions. The J format, which is just for jumps, and between I format, R format, and J format, that's all we have. That's all you have to know, those three formats. And so jump gives us our third format. So we're going to look at how these work individually. We'll look at the jump first because it's a little bit easier to understand, although there are some complexities because MIPS has these little complexities, but we'll see. So we're going to replace the program counter with a new value, and usually that is for a subroutine, right? Go away and execute somebody else's code. Syscall is kind of like a jump. We're going to start to execute operating system code instead of executing our own code. And this is sort of like a go-to in programming, in higher level programming languages. You've probably never used a go-to because it's considered very bad programming practice to use a go-to. The reason it's bad programming practice is because it's hard to trace a program that's full of go-tos, because go-to then has a target that it's hard to sort of follow back from where it comes from. If your program suddenly starts executing this instruction, you don't know how it got there. Could have got there from this go-to or that go-to or that go-to. It's difficult to debug a program with go-to. However, in assembly language, go-to is a fundamental characteristic of the way we do control flow, the way we go to a subroutine, the way we come back from a subroutine. These are done with jumps, and so you need to, around that jump, you need to be very careful about how you specify how to get there and how to get back. And that's part of why assembly language programming is a little bit more challenging than regular high-level language code. And that's part of why we write in high-level language code to take care of all those little bits and pieces. But this is how it works at the low level, which is what this course is all about. So the program counter tells you where in memory the next instruction is. And so we're going to change the program counter to allow us to execute some other instruction. Okay? So again, jumps like a go-to, bad practice in high-level language, but we will do it here because that's how these things actually work. So we want to jump to some new address, right? The addresses are 32 bits wide because that's the memory space of a MIPS machine. We need to put a new value into that. There's a couple ways to do that. We can put a value from a register because registers are 32 bits, but we don't want to have to do that. We want to be able to allow the assembler itself to put a value into the program counter directly. And we actually call this direct addressing. That means we put a new address, a complete fresh address from the assembler, which means it lives in the instruction memory. We put that into the program counter. The problem is instructions are 32 bits wide and addresses are 32 bits wide. So if we want to say an instruction that says put these 32 bits into the program counter, we don't actually have 32 bits. We have 32 minus 6 because opcodes are always 6 bits. And you can't get away from that because until you read the opcode, you don't know what instruction you're executing. So we have to use those 6 bits as an opcode, and then the remaining bits, 32 minus 6 is 26. The remaining 26 bits are going to be used to generate a 32-bit address, and we'll see how that works. It's a little complicated, but I'll walk you through it. Other assembly languages get around this problem by allowing instructions that are longer. Say a 6-bit address and then a complete 32 or a 6-bit opcode and then a complete 32-bit address. You could then use that to just dump those 32 bits into the program counter and go. MIPS doesn't allow variable length instructions, and so we have to do this special way. Now we then have a 26-bit immediate value, and we have to build into that a 32-bit address. And there's two little tricks that we use. First is we know that the bottom 2 bits of any instruction address are 00. Why do we know that? Well, instructions are 4 bytes long. Each memory address points to 8 bits. And so it takes 4 of those to specify an address. And those addresses are always aligned because you don't have anything other than those 4, 4, 4, 4. And so if we start at 00, the next one's also going to be at 00. And so we can just say we know it's going to have 00. And then we've saved 2 bits. The top 4 bits, then, we're going to use the existing top 4 bits of the program counter. It looks like this. And again, the complexity of this is a little frustrating, but I'll try to walk it through in a couple different ways just so you understand why this works the way it does. So this is a new instruction format called JType. Okay, the opcode is still 6 bits. The remaining 26 bits are going to be what we call the jump target address, or JTA. This is going to be most of the new value that we're going to put into the program counter that will then be used to point to the new instruction that we're going to execute. We're going to take 00 at the bottom because every instruction is word aligned. And then we're going to just say the current value of the program counter, whatever that happens to be, we'll take the top 4 bits, and that'll be good enough. That'll get us most of almost anywhere in the complete memory space. It won't get us everywhere, right? If our new address starts with something other than whatever the current program counter is at, then we're going to need a different way to do this. But for now, this will be good enough. And so for most jump instructions, this is what we will do. If it's not enough, then we have another kind of instruction called jump register. This is where we jump to a value that's specified in a register. And this is nice because registers are 32 bits, addresses are 32 bits, so we can just say we can generate an address in a register, which takes a few extra instructions to do, but then we can jump anywhere. And so those are the sort of 2 options for jumping. Jump, which is just the letter J, and then JR, which is jump register. And we can target any address in the memory space that way. So with those 2 instructions, we have all of our different instruction formats. We have R-type, which we already saw. We have I-type, which are the immediate values, and we use that not just for immediate operations, but also for loads and stores. And then we have jump target address, jump type, J-type, right? So 3 types, R-type, I-type, and J-type. And the J-type is just the entirety of the instruction is taken up by the jump target address. And that's the only format you'll ever have to learn. We might do some floating point stuff later, but we'll see. Everything else is based on those 3 formats. And so with that, if I give you an instruction, you should be able to tell me the 32 bits that correspond to it. So all instructions in MIPS are going to be one of these 3 formats. And we're going to look at branches in a little while. Branch instructions use immediate format, on other instructions as we go. And then in the next few sets of notes, we're going to look at the branching, which again has a lot of detail to it. So we're going to spend more time on it. And then we also are going to look at all of the different kinds of data structures that we can use, how we do subroutines, why our registers are named the way they are. There's lots and lots of additional details to look at. So for the end of this set of notes introduced the machine and gave you the basic format of the instructions that are in MIPS. You should be able to, if I give you a MIPS instruction, you should be able to look at this machine and tell me what the value of each of these multiplexers are for that instruction and how data flows through this machine, right? Because now you know the different formats, how they work, and you should be able to tell me how that happens. Additionally, you should be able to, if I say I have this machine and I want it now to do something else, maybe I want it to do a different kind of addressing, maybe I want it to do shifting or whatever, you should be able to add that functionality to this machine by adding additional boxes and wires and control points and everything to make it implement that functionality. Because that was the incremental design we did, and that is the way that we're going to finish building out this machine.